In section 4.3, we will talk about the right-angle theorem. Let's suppose we have the diagram as shown, ABC being a straight angle, and we're given that angle ABD is going to be supplementary to angle CBD, and we're also given that angle ABD would be congruent to angle CBD. So knowing those givens, what can we conclude? Let's think about this algebraically for a second. We know that a straight angle adds up to be 180 degrees. We also know that the two angles will be congruent. Now, let's say we don't exactly know what they are, but since they're congruent, we can label them with the same variable. But we do know, like we previously stated, that the sum of the two angles will equal 180 degrees. If we go ahead and solve this, 2x equals 180, x equals 90 degrees. Therefore, we can conclude that each angle is 90 degrees, or a right angle. So the theorem we can take out of this is, if two angles are both, that's the key thing, supplementary and congruent, then they are both right angles. Let's look at our first example. We're given the diagram on the right along with the following information. That line segment MN is congruent to line segment NP. Line segment MS is congruent to line segment NS. What we are trying to prove is that line PS will be a perpendicular bisector of line segment MN. Correction, this first one should be line segment NP. So the diagram will look as followed. Now, if we think about what we're trying to do, we're trying to get PS to be a perpendicular bisector of line segment MN. Starting with just the basic being a bisector for line segment MN, that would mean that we would want that line segment to be divided evenly right here. We would want MF congruent to NF. Notice what triangles those are a part of. It would either be a part of the top two triangles, the line segment would be here and here, or the bottom two triangles where the line segments would be congruent here and here. But if you look at the information, we don't have quite enough to go directly to those triangles. So we'll do what the book called as a detour. We'll go to the bigger triangles. We'll do this triangle with this triangle because you can see that we have two pairs of congruent sides, and it's pretty easy to state that PS is congruent by itself based on the reflexive property. Now that we have these triangles congruent, we're going to look for other corresponding parts that might overlap with those smaller triangles, which might give us more information to prove the smaller triangles congruent. If you look, angle MSF and SFN are both part of the triangles we just proved congruent, but also part of the smaller triangle right here. So we'll state that those are congruent based on the CPCTC. Now let's still continue to look at this smaller diagram. In that smaller diagram, I have these sides congruent now, these sides congruent, this angle, and this angle. Similar to the first triangle, we can now use the reflexive property right here to say that line's congruent to itself, and there you have side angle side to prove the triangles are congruent. Now that we know that those two triangles are congruent, we can use CPCTC to now say that this side is congruent to this side. We can also use CP/CTC to say that this angle right here is congruent to this angle. The blue highlighted will take care of the bisecting part of the proving the line is a perpendicular bisector of MN. So then why did we go ahead and say that these two angles are congruent to each other? Well, if we establish that they're congruent and they're supplementary, that will conclude that they are right angles, which would then conclude that it would be a perpendicular bisector and not just a bisector. Since I've now established that those two angles are right angles, and that those two segments are congruent, I can now go to the conclusion that line PS is a perpendicular bisector of MN.